The James Webb Space Telescope just found a galaxy that should be spinning, but it isn't, and nobody really knows why. There are trillions of galaxies out there in the universe, and almost all of them are spinning. Our galaxy of stars, the Milky Way, is spinning. Andromeda, our nearest neighbour, is spinning. And once a galaxy gets its spin, it keeps it. There's no friction in space to slow it down or stop it. Instead, it takes something really violent and catastrophic to strip a galaxy of its spin. Like a collision of two galaxies. When they merge together, all the stars and gas get scrambled up and sloshed about, stripping away some of that nice ordered rotation. And we think that over billions of years of repeated interactions and collisions, every merger strips away a little bit more of a galaxy's spin, until you get left with something known as a slow rotator. A galaxy that has finally lost most of its spin. But a brand new research paper using data from the James Webb Space Telescope, JWST, that was published recently by Forrest and collaborators, has discovered one of these slow rotator galaxies existing when the universe was less than 2 billion years old. That goes against all of our best models of how galaxies evolve over time. There shouldn't have been enough time for all of the spin to have been stripped away from that galaxy yet. So, what is going on here? Well, we're going to dive into all of this in this video and chat first about why galaxies have spin and how they lose it. Then second, what Forrest and collaborators found using JWST. And then finally, the best ideas we have to explain this discovery and what's going on. So let's start with number one there, why galaxies have spin. And for that, we have to go back to the beginning, to the very early days of the universe when all there was a hot, dense soup of matter and energy. But crucially, that distribution of matter in the early universe isn't perfectly smooth. There are ever so slightly denser areas and ever so slightly underdense areas. And having those ever so slightly denser regions means that more matter will start to clump there under gravity, and slowly but surely gravity will start to pull material in from the surrounding regions and set it moving. That is the seed of a galaxy's spin. And so it's in those denser regions that galaxies first start to form, but they are incredibly messy. Gas is flooding in from all directions, and you get massive bursts of star formation driving huge outflows of gas. So everything is turbulent, everything is disrupted. So the spin is there, but it's very messy and turbulent, and the shape of the galaxy is very irregular. Going from that to the thin, beautiful, spinning spiral galaxies that we're used to seeing around us today with that settled rotation, that takes time, and a lot of it. Billions of years of relative calm for the gas to settle, for the disk of stars to flatten out, and for the structures we recognize today to pop out. Once that happens, what's known as the Hubble sequence emerges. This is the classification system that we use to organize galaxies by their shapes. And so on one end, we have those beautiful spiral galaxies, and on the other end of the spectrum are elliptical galaxies. These are some of the most massive galaxies in the entire universe, and they are just giant blobs of stars. There's no flat disk of stars, there's no beautiful spiral structure, it's just one big sphere of stars. They're rarer than spiral galaxies, and crucially, these aren't spinning, or at least they're not spinning very much. The stars are still orbiting around the center of the galaxy. That's how the galaxy holds itself up and doesn't just collapse under gravity. But they're all orbiting on different planes and in different directions. It's more like a swarm of bees in there. There's no order to it. So while the stars are still orbiting the center, the galaxy as a whole isn't really spinning. And we think that that's due to these repeated galaxy mergers over billions of years. Even the effects of a single galaxy merger can take over 1 billion years to be fully appreciated in simulations. To slowly strip away the spin and to scramble everything up to give you that big blob shape. And one of the biggest unanswered questions in this field of galaxy evolution is, when does this Hubble sequence emerge? When did galaxies go from being messy and turbulent and irregular to the recognizable shapes that we see around us today? And we can actually answer questions like this with the data from our telescopes, and that's because light takes time to travel to us, traveling through the universe at its set speed limit of 300,000 kilometers a second. It means that the more distant a galaxy is, the longer the light has been traveling through the universe for. And so we get to see galaxies as they were billions of years ago. We get to observe galaxies evolving from what they used to look like to what they look like today. But with the Hubble Space Telescope, there was only so far back that we can see because distant galaxies just get too faint for us to be able to spot with Hubble. But then in 2021, the James Webb Space Telescope launched, JWST, and with its bigger mirror to collect more light, it almost immediately started finding lots of spinning spiral galaxies at points in the universe's history where we didn't expect to find galaxies that settled or organized or that structured. My own research with JWST has even shown that you can get disk galaxies without any spiral features showing up at even greater distances that are perhaps the first stage in going from that messy, irregular structure to something more ordered. I've made a video on that research paper that I published before on my channel, which I'll link in the video description down below. So those disk galaxies with ordered rotation earlier in the universe's history were the first surprise from JWST. And now, Forrest and collaborators have given us the second surprise, which brings me to part 2, what Forrest and collaborators actually found using JWST. Because while JWST has found galaxies that have more spin than we expected in the early universe, Forrest and collaborators have found a galaxy with less spin than expected. The galaxy is called XMM Vid12075. As usual with astrophysics, it's not exactly a poetic name, it's just a catalogue name of all these different numbered sources that have been found in a survey. So if you would like to pop your suggestions for a better colloquial name that we can refer to this galaxy as, pop your suggestions down in the comments below. The punnier, the better. Now, this galaxy had already been flagged as potentially interesting a few years ago in a survey called Magazine, the Massive Ancient Galaxies at Redshift 3 Near Infrared Survey. That survey used the Keck telescopes in Hawaii to reveal that this was one of the most massive galaxies known in the early universe, already containing several times the amount of stars that the Milky Way galaxy has today, yet much earlier in the universe's history. It also didn't appear to be forming any new stars. It was what we call a dead galaxy, so we say that the star formation has been quenched. Something that we know is tied to that slow process of many mergers transforming a galaxy. Again, this is something I've worked on before in my research, looking at the different way that fast and slow rotators stop forming their stars. But just from an image of the galaxy alone, just from its shape, you cannot tell what the stars are doing. Something that looks like a giant blob could actually still have some ordered rotation. But to get at that information of what are the stars actually doing in the galaxy, you need to take a spectrum of the galaxy's light. That's why you take the light and split it through a prism or a diffraction grating so that you can get the rainbow of colours that it's giving off, or how much light at each wavelength or colour of light you're receiving. Now, thankfully, for what is pretty much the entirety of astronomy, specific elements in the periodic table give off very unique wavelengths of light, or can absorb very unique wavelengths of light. So emission comes from gas that's lit up by nearby stars that are forming, and absorption comes from elements in a star's atmosphere absorbing light before it makes it to the surface. So in the spectrum of a star-forming galaxy, we get a lot of spikes at those unique wavelengths, and in a spectrum of a galaxy that is no longer forming stars, we get a lot of dips in the spectrum. And it's thanks to those spikes and dips being at very specific known wavelengths that we can track what are the stars doing, how are they moving. Because if a galaxy is rotating, then one side of the galaxy will be coming towards you as one side of the galaxy moves away from you. So we'll get a Doppler shift on each side, like what happens to the sound of a siren when an ambulance races past and its pitch gets higher coming towards you because the sound wave gets squashed, and then the pitch gets lower when it moves away from you because the sound wave gets stretched out. The same thing can happen to the starlight as the stars are moving. So on this side of the galaxy that's moving towards you as it spins, the starlight gets squashed in its wavelength. So the specific location of that dip or that spike gets shifted this way. And then as these stars are moving away from you on the other side of the galaxy, the position of that spike or that dip gets shifted in the opposite direction. So from the position of where that spike or dip is relative to where we think it should be, we can then track how fast the star is moving either towards or away from us and map out the rotation of the galaxy. And here's where it gets really cool, because JWST has an instrument on board called NIRSpec, which has a mode of observing called an integral field unit, or an IFU, which instead of just collecting one single spectrum from the whole galaxy at once, an IFU tiles the galaxy with little pixels, each one giving you its own spectrum. And so you get a 3D data cube with a huge amount of information. You can either think of it as an image at every single wavelength or a spectrum at every single pixel. And that's what you use to map out how fast are the stars actually moving in different parts of the galaxy. That's what's plotted here. The blue colours show you where the stars in this example galaxy are moving towards you, and the red colours where the stars are moving away from you. And you can really nicely see that pattern. Or compare that with this example where the galaxy isn't rotating and there's no pattern to it at all. Those examples I showed though were for galaxies that were really nearby. So it's incredible that JWST is able to do this for galaxies at such incredible distances. We're talking about resolving the kinematics of a galaxy 11.5 billion light years away. That would have been unthinkable 10, even 5 years ago. And so Forrest and collaborators managed to use JWST to map the stellar velocities inside XMM VID1 2075 and found nothing.
Nothing.
Or almost nothing anyway. You can see how there's no clear pattern of rotation in the data. Compare that to the two other galaxies they observed, where you can see how one side is coming towards you and one away from you. Whereas in XMM VID1 2075, there's just no structure to how the stars are moving. They're moving randomly in all directions. Now, to actually quantify this properly, rather than just looking at visualized data like this, we use something known as the spin parameter, or lambda RE. It essentially measures the balance of ordered rotation versus random motion within a galaxy's effective radius, hence RE. For fast rotators, at least in the nearby universe, that number tends to be above 0.3, so very much dominated by ordered rotation. Whereas for slow rotators in the nearby universe, that number tends to be around about 0.1, 0.2, so dominated by random motion. But you also have to consider what's known as the ellipticity of your galaxy as well. Essentially, what angle are you looking at it at? Because yes, a big sphere of stars will look completely round, but also a spiral galaxy, seen face on, which is being demonstrated beautifully by this plate here, will also be completely round, but won't have any detectable rotation because the stars, if they're rotating like this, nothing is coming towards you or away from you, so you won't be able to detect any rotation. So here is the ellipticity plotted against that spin parameter. And this region in the bottom left is where you usually find true slow rotators. And XMM VID1 2075 has a spin parameter of 0.123, suggesting it is firmly in slow rotated territory. But there are a couple of different definitions that people use. That's what's shown by the different coloured lines there, meaning it is sort of right on the edge of the boundary. So to rule out whether what they've seen was actually a true slow rotator and not just a fast rotator disk galaxy seen completely face on, Forrest and collaborators carefully modelled the shape and the light distribution of this galaxy. And everything they found, from the inclination to how the starlight was concentrated and distributed in the galaxy, to how much mass that the star's movement suggested was there, all supported the idea that this galaxy was not a disk galaxy viewed perfectly face on, making XMM Vid12075 the first slow rotator found at a time when the universe was less than 2 billion years old. Somehow, in that limited amount of time, that galaxy has already had its spin stripped away. And that directly challenges our best hypotheses that we have for when and how the most massive galaxies in the universe came to be. Which brings me to part 3, the best ideas that we currently have to explain what's going on. And I think this boils down to 2 main frontrunners. Either a single cataclysmic merger was all it took to strip the spin away, or something else is responsible for stripping away the galaxy's spin. So let's start with that first option. Instead of the gradual draining of the spin through repeated galaxy interactions and mergers over billions of years, what if one single cataclysmic collision between 2 galaxies was responsible? To get this to work though, the rotation of the 2 galaxies that merge together have to be going in exactly the opposite directions, effectively to cancel out the spin. Now there is evidence to support the idea of a merger in this galaxy. So if you model how the light is distributed in this galaxy and take off that model from the image, you get left with some light from this very wonky structure, the kind of thing that you typically see in recently merged galaxies. It acts kind of like a fingerprint to be like, yes, something violent happened in this galaxy's past. The catch though is that for 2 galaxies to have nearly perfectly anti-aligned spins and also similar masses as well to have that cataclysmic effect, that combination is very rare. Not impossible, but just very unlikely. The second option there is if something else other than a merger did the stripping of the galaxy's spin. And simulations have suggested that it could be an infall of gas from all directions of equal amounts. That would help to randomize the orbits of any stars that formed from that gas. And the Magneticum simulation, which actually does manage to form slow rotators this early in the universe's history, finds that their star formation was actually quenched in this way. So how do we tell which of these is the correct explanation? Well, like with so many studies in astrophysics, the answer is to find more things like this, to actually get statistics on how common are these things at this point in the universe's history. Was this a fluke, or are there quite a lot of them? And do they all show evidence of merger history in their past? And thankfully we have JWST to be able to do this now. There's lots of this IFU style data being taken of galaxies at great distances by JWST to help answer a multitude of scientific questions, because there's a lot of information contained in those 3D data cubes. So we can just now add this question to that ever-growing list as well. And this is why I love JWST, right? It just keeps surprising us. It's showing us once again that the early universe is just not what we thought. It's maybe less chaotic than we thought, or maybe it's more efficient at building things than we thought. Either way, this era of discovery that we're living through right now, I just find it so exciting, and I hope that you do too. So if you enjoyed this and you stuck around to the end, thank you. Please consider subscribing if you haven't already, because there is so much more JWST science coming, and you can bet some of it might even be more surprising than this was. But crucially, how that matter is distributed... Oh my god, why is my eye going crazy? You're fine. Why are you watering? Windows shut. Tree hay fever season is supposedly over. I need something like a CD right now. Do I even have a CD to demonstrate this with? I don't think I do, you know. Like a DVD, or I must have some sort of like software-y thing somewhere. Hang on a minute. No CDs or DVDs in the house, but I did find a plate. So